Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecraft. And in this module, we are discussing the risk assessment and the reliability theory which are relevant to the spacecraft or space missions. So, in the last session, we discussed what is the satellite service availability. So, in order to have an in order to have a continuous satellite service, so what is needed considering two cases. The first case we considered it is there is no backup satellite in the orbit, and then in that case in order to have the satellite service availability, the number of satellite n's which are required to be launched per year. So, this is the number of satellites n required to be launched in the required period L. So, this we derived in the last class. So, where as already said L is the required time and then P is the probability of a launch success and capital T is the mean time to failure and capital U is the maximum lifespan or maximum life of the satellite. So, I will delete this here. So, required and required in the required period L. Okay. So, and then the availability of the satellite we expressed by this expression. So, where TR is the time, it is the time required to replace a satellite, the time to replace a satellite, and P and T is the same as used in this equation. Now, when there is the backup satellites in orbit, then we need the number of satellites in the required period L, it should be twice. So, this n is just double of the quantity of the satellites which are required to be launched in a period of L. So, here it is just getting doubled, and we explained that is the availability in this case is, this is the expression, and we have seen yesterday with two examples, that is the availability, it definitely increases whenever we have the backup in the satellite. Okay. So, using those equations whatever we discussed in the last class. So, we can, this table is made from that calculation. So, if you consider there are different cases are given of the maximum lifetime 5 years, 7 years, 10 years, and then the mean time to failure, that is MTTF 10 years, 20 years, 20 years, and then once you know these two quantities you can calculate what is the mean lifetime. So, in the first case it is 3.9 years, then 5.9 years and 7.9 years. Okay. So, as it can be seen that when this MTTF is increased, the mean satellite lifetime is getting increased. Okay. Then the parameters time to replace the satellite, and if you have the probability of the launch success, then we can calculate the launch rate. So, this example yesterday we took, this example, this is the example yesterday we took, and now we will discuss from here considering these two cases. So, if you consider this the first case, that is the availability in no backup case, the availability A is given by 0.9722. Now, you consider that you have a required period, you want a service that is the service period is 10 years, then the service if this is the availability, then the service will not be available considering L is equal to 10, then you can calculate it will not be available for. So, it is 1 minus 9.722 multiplied by, if I write it in terms of months, then 10 years means 112 months. So, this will give you, if you can calculate this, so this will give you something like 3.4 months. This is quite a big number. Now, let us consider for the backup case, when there is the backup satellites are available. So, in backup case, so we had A is equal to availability, it got improved and that is the value was 0.9987. So, now if I calculate the unavailability, so the unavailability, that is B will be B in 10 years, it will be B means that is the unavailable period. So, this is 0.9987 multiplied by 120 and this comes to be equal to 0.18 months. And if you take, if you convert this in days, so this will be approximately something like 5 days. This is approximately 5 days. So, you see how with the launch with the backup satellites, your availability, satellite availability has improved from 3.4 months to the 5 days, but at the cost of more number of that is the cost is obviously here this satellite, each satellite is having a backup satellite. So, that way the cost will increase, but obviously, we are having a better the availability has improved drastically. So, in order to limit the unavailability, what is needed to be done? So, from this table if you see it carefully, so what you need to do, that is it needs, this is the first thing is requires the presence of backup satellites satellites in orbit. So, it has to be 4 to 6 replacement launches. So, this is one criteria. Other criteria is that it should have a MTTF. So, satellite overall, that is that mean time to failure, apart from those system which like propulsion system and all those things, apart from the other system, it should have this MTTF at least 10 years, at least 10, 20 like that. So, we have seen that whenever the MTTF T we are increasing, we are able to increase the mean time to failure of the satellite within its maximum lifetime. So, that is why the requirement is that the satellites need to be designed with a failure rate which is less than 10 to the power minus 5 hour. So, if you convert it into feet, so feet will be, it will be 10 to the power 4 feet. So, 1 feet is equal to 1 FIT is equal to 1 billion hours. So, it is 10 to the power 9 hour. So, you can convert 10 to the minus 5 hour is equal to 10 to the power 4 FIT. So, this was whatever we discussed in the last session. Now, today's session will start with the system reliability. So, a system always consists of the subsystem, and subsystem consists of the components and devices. So, that way we will start with the system reliability, then we will go to the components and material, everything. System reliability depends on a subsystem reliability, and subsystem reliability will depend on the components, materials, devices, everything. So, we will consider that is all the subsystems are in series, and then we will consider a redundant subsystem. Redundant subsystem means the systems are in parallel. Now, as you will consider, because here we are discussing the satellite system. So, in satellite system, most of the systems are series, until and unless we are not putting a redundant for the critical components, there can be a redundant the subsystem like the TWTA. So, there will be redundant TWTA, but there are many the other components, like if I consider a typical satellite communication, it will start with the antennas, then there will be the transceiver. So, and then there will be the other this down converter or up converter, all these things will be there, and then this total the transponder chain, if you see, most of the components they are in series. What does it mean? That if any of the components in the series it does not work. As for example, if the antenna fails, then the whole the mission will fail, or suppose a system like a onboard processor, if it does not work, then the whole system will not work. So, this is the way the systems are built. So, systems are built keeping the subsystems in series, or it can be in the parallel also. So, we will consider the series as well as the parallel subsystem. So, whenever if the systems are in series, so the correct operation of each system is to be indispensable for the correct operation of the system. So, so the calculation of the system reliability is performed from the reliability of the system elements, that is the subsystem. System element means the subsystem. So, there is already I said all this are in series. So, whenever the systems are in series, so if any one fails, this total this chain will fail. Now, subsystems in parallel, see parallel means this is you can just consider a typical input and output. So, just like considering the electrical circuit concept, whether a circuit. So, suppose you just consider a electrical circuit keeping components in series. Suppose if one component fails, so there will be open circuit and the circuit will not work. But when you are putting the components in parallel, so what will happen? Even if this does not work or anyone, suppose you can just consider this as an electrical bulb. So, there is the supply is there. So, if the things are in parallel, so suppose if any one is not working, it will not affect the performance of the others, but unlike the case here. This is a system where is the series parallel system. In fact, this is the most this is the practical way of making a system, where here it is shown this is we are showing some N systems, and in N there are like the first one is having N1 in parallel and 2. So, what does it mean? That this system, suppose if I consider the first subsystem. So, first subsystem there is the parallel N1 components. So, any one can work. So, basically I can say these are the redundant So, there can be 2, 3 like that redundant system. So, it is just a general diagram, but in practice whatever is the the requirement, like a if it is a like a TWTA, so it will be two redundant system like that. So, we will consider each type one by one. So, first we will consider that is the system in series. So, we will this is the system 1, 2, 3 up to n, and let each subsystem or each element also I can say each subsystem subsystem 1 to n has the corresponding reliability functions these are the probability functions. So, it can R 1, then R 2 and R n respectively. And further let us assume that this element, these subsystems are they are statistically independent. Okay. So, statistically independent means if I take assume that these subsystems are statistically independent, that this subsystems are independent. So, if it is statistically independent, that means if I take any the probability of the ith element and the probability of the of survival, that is of the jth element, and then if I take the intersection, that is the end operation, then I should be able to write it like R I R j. So, considering this, the system reliability system reliability can be written as so, the system reliability is ensured when all the sub elements 1 to n should work. If any one fails, then the total the chain will fail. So, under that condition, the system reliability will be the multiplication of the probability. So, we can multiply it because this is an AND operation. AND operation means it has to be both. So, if there are all the elements should work. So, this is basically an AND operation. So, AND operation as I said like this. So, these are independent. So, directly I can multiply it. So, the system reliability R s will be the multiplication of R 1, R 2, R 3 up to R n. Now, let us further assume that each subsystem has a constant failure rate, failure rate will designate it like R I. Okay. So, then I can write R s is equal to so R 1 will be equal to, so in that case our R I will be equal to e to the power minus lambda I t. Then I can write the system reliability. So, I can write the system reliability R s is equal to e to the power minus lambda 1 t into e to the power minus lambda 2 t then e to the minus okay, and then I can write R s is equal to. So, this is equal to e to the minus lambda 1 plus lambda 2 into t. So, now you see from this it is shown that the system has also a constant the failure rate, because here this is just the algebraic sum. So, I can say that the failure rate of the system is the summation of the failure rate of the individual the element. So, if lambda s is equal to, if lambda s is the constant failure rate of the system, then I can write lambda s is equal to lambda 1 plus lambda 2 plus lambda n. Okay. And then, so this is the failure rate of this system, and if you know this what is the constant failure rate, then the mean time to failure. So, we can calculate the mean time to failure. So, mean time to failure will be equal to 1 by lambda s. So, this is equal to 1 by, I can get a summation of I is equal to 1 to n, and this is lambda I. Okay. So, you can see that here obviously the failure rate will increase, giving rise to this a lower value of the MTTF. So, whenever you are putting this many systems in series, the overall reliability of the system will definitely it will decrease. Okay. So, now we will consider practically all the system will not be in series, there will be some the redundant system. So, we need to modify our whatever we have seen, that is the finding the reliability at the system level. So, there is this is that is called the active redundancy. Of course, we will call it static, we will use this term the static redundancy. Static redundancy means we are not using any switch. So, as if in the chain both the elements are it is active, and it is said that whenever, or it is assumed that whenever one system is, when both the system will fail, then only the failure will be there. So, means the systems are in parallel. So, here what we will consider that is two systems, they are the two are the independent and they are having reliabilities R 1 and R 2, okay, and it will operate satisfactorily when any one of them, either both or any one of them. Okay. So, I can write this probability, that is system probability R s. So, I will consider, or here let us use again R s only. So, R s will be equal to R 1 plus R 2. So, there it was here it is an OR case. The previous case when it was in series it was an AND case, but here it is OR case, or I can write in terms of a call a system failure, then I can write is F 1 into F 2, means the system will fail when both fails F 1 and F 2. Okay. So, so I can write both way also. If I write this F s is equal to, then R s will be equal to 1 minus F s. So, in that case I am having 1 minus F 1 will be 1 minus R 1 and then 1 minus R 2. Okay. So, I can get from here R 1 plus R 2 minus R 1 into R 2. Okay. I can get from here also whenever it is OR case. So, I can write the probability of two events A, U, B, if it is OR case, then I can write P of A plus P of B minus P of A intersection B. And in this case, since it is the A and B are independent, so I can write P A into P B. So, we are getting the same thing here. Okay. So, now if I consider a constant failure rate, so I can write again considering constant failure rate, I can write R s is equal to, so it will be R 1 plus R 2. So, I can write it e to the power minus lambda 1 t, then it will be e to the power minus lambda 2 t, then it will be e to the power minus lambda 1 plus lambda 2 t. So, this is the system reliability, and obviously, if you see now I cannot write this as a e to the power the way we write it for the series case. So, we need to now find out what will be the the failure rate and what will be the MTTF. Directly we cannot find it out. So, if I want to find out the MTTF, what I need to do, I need to integrate this R s, then only I can find it out. So, we will continue with this and let us end here. Thank you very much.